distance. So the question is, what is delta x, right? That's the question. And again, just so you know where I'm getting this from, this is example 4 on page 4 of lecture 4. Whoa, example 4 on page 4 of lecture 4. It's got a certain ring to it. So here we go. Final velocity squared equals to initial velocity squared minus 2.0 meters per second squared times delta x. What's the final velocity in this situation? It's not. I didn't tell you. You got to use that thing we used earlier, common sense, right? I heard a 0. I like a 0. So what we got is 20. So yeah, that's 0. And that gives us delta x is equal to v naught squared divided by 2.0 meters per second squared, also known as 400 meters squared per second squared divided by 2 meters per second squared. I like the units canceling. That's a good sign, right? I'm not trying to instruct you with yet another algebra mistake today. I'm on the straight and narrow, it appears. And what's that give us? 200 meters is apparently the stopping distance. Oh, what'd I do? Aw, man. You guys got me. Excellent. I'm very happy to hear that. Right. You are complaining that I have neglected this 2, and that is a very, very good comment. Thank you, guys. And so what's that do to me? That makes this a 4. The negative's gone because I had to add that to the other side, and then I divided by the 4 meters per second squared. So that looks like 100 meters. So the stopping distance for that would be 100 meters. Yeah. Let me, I'm going to use my projector here for just a second because we're almost out of time. And I just wanted to tell you a few more just conceptual things I always try to say when I'm teaching physics. These are just important kind of checkpoints to be aware of. Because in our common speech, I mean, I've already pointed out today that we have this trouble that, I don't know if it's a trouble, but it's just a reality that often we use the word long to either mean distance or time, right? Like, how much longer is this trip? What does that mean? It could actually mean how many minutes. It could mean actual physical distance, right? Depending on who asks it. Whenever my children ask that, I always tell them 2 minutes. It doesn't matter if it's a trip to Disney World and we just left the driveway. I will say 2 minutes. I've taught them not to ask me how much farther it is. So that's one abuse of language that you have to be aware of. The other abuse is the confusion between acceleration and velocity. Something speeding up. What's that mean? Does that mean acceleration? Probably it means acceleration, but I'm telling you, there's a certain ambiguity. There's just a confusion between velocity and acceleration in common speech. So here's a few different cases that I thought would be fun to look at for just a second. We've got a few minutes left here. If you have a ball dropping, you could have, actually the ball's not dropping. With my stupid picture, which the ball's dropping, the velocity's going up. That makes sense. Typo, right? That should be, I would drop my laser, but I value my laser. You know, here's something I don't value. Dropping, the velocity points downward. Acceleration also points downward. So actually the velocity and acceleration should both be pointing in the same direction if I hadn't made that most annoying error. Car speeding up. Well, the acceleration and the velocity are both in the same direction, right? Right? All right. If you throw a ball upward, the velocity is upward, right? But what's the acceleration? Downward, right? Did you guys ever see Fringe? You guys know what I'm talking about? There's this show that fox let survive for about 4 years. It's about parallel oh, I'm sorry. I won't spoil it. Anyway, this show, one of the episodes, gravity goes the opposite way. So people have to like wear shoes that keep them from flying up into the sky, right? So if like G went the other way, if you threw a ball up, it'd be like, oh man, I just lost the ball again. But, like to the universe. So that doesn't usually happen. Usually when we throw a ball up, the acceleration brings it back down, right? And then in ideal car braking, we have the speed would be going this way, and the acceleration would be going the opposite way. I say ideal. Up here I said constant acceleration. Is actual acceleration for a physical car or braking for a physical car that you're driving in actually constant? Probably not. It's more complicated than that, right? The acceleration is changing. Do you know what that's called? What's the change in the acceleration with respect to time? Don't know? I tell you, but I don't want to be a jerk about it. It's called the jerk. The change in the acceleration with respect to time is known as the jerk. I think this question I more or less worked last time. This one's complicated. Let's just get past that for a second. Here's a pretty good one. Two stones are dropped from a cliff. Yep. Oh. They were illustrating, like I thought they were raising their hands, but they're just talking to each other like this, but it was an illustration for their conversation. It's confusing for me for a second. All right, it's fine. I'm over it. Moving on. Both stones are dropped. That means that if you drop things, their initial velocity is what? 0. And the second stone is dropped 1.6 seconds after the first. How far below the top of the cliff is the second stone when the separation between the stones is 36 meters? This question can also be asked in the form of like a window. You can imagine that this is a window and that, I don't know, there's various ways to, I'm going to shut up about that, but all right, so here's the setup. I called one stone A, I call the other stone B. The A stone has the initial y0 minus 1/2 g t minus 1.6 seconds squared. The initial stone is y0 minus 1/2 gt squared. See, the difference is the motion starts after 1.6 seconds, so I have to do t minus 1.6 to account for that 1.6 second drop in the formula. The time of flight for A is t minus 1.6 seconds, whereas the time of flight for B is just t. I made y equals 0 down here. I'm also given that the distance between YA and YB is 36 meters. So what I do then is I put this equation and that equation down here, I do algebra. And what's going to happen is, quadratic. Is it a quadratic equation? Nope, not quite. What happens is that I think the t squareds end up canceling, which is ever so lovely. And then you can just solve for t and get 1.4936 seconds. What's this? I think that's the, what's that? Yeah. Here's another one that's a little bit tricky. I'll just shut up with this. I'm just saying, if you need extra examples beyond the book, these notes aren't bad, I think. What's that? I posted a link to my, I'll send it in the announcements. I mean, I'm going to send you guys a weekly announcement anyway. I'll send it in the weekly announcement. This one's about a pair of subway cars passing a certain point. This is a lot like one of your homework problems. It might be helpful. Again, it involves the average velocity formula. So, all right, I'm going to shut up. Have a good week, you guys.